With these next series of videos over the next 3 weeks or so, we're going to actually transition to talking much less about how to write SQL queries, although you still will be having to write SQL queries in the homework and for the projects. But what we're going to spend a lot more time talking about is probably the most essential part of databases, and that is that of transactions. These are what make databases so much more powerful than just complicated ways to store data in a file. All right, but before we get into transactions, I want to talk about first why databases even support transactions to begin with. And for that, I want to talk a little bit about performance. And once again, performance isn't a huge aspect of this class. I'd much rather you understand how and why things work than to worry about exactly like how many seconds each sort of type of query will take. But so let's think about some example databases that you might care about performance. For instance, one very common use of a database is as a web content server, that's serving out HTML pages and files and YouTube videos, or managing the Piazza forum or something like that. Or, for instance, the HackerRank leaderboard that's showing the high scores from various programming competitions. Or, a database that holds medical-related information, and that information is being made available to insurance and to doctors and to patients. Or, if you're running a tax accountant office and you have to store all of the data regarding all of the auditing and payments and so forth. And the important thing about basically almost every database you can write, there are two sorts of things that matter with regard to performance. One is throughput. It's basically how many requests can the database handle per second. Can it handle 100 people trying to connect to a web page at the same time, or 1,000, or 1,000,000? Or is it only able to handle, a couple requests a second? And so it acts as a limit to how quickly you're able to serve web content. So once again, the more requests a database can handle, aka the more queries a database can handle, the more useful that database is. If it can only handle one query a minute, it becomes much more painful to use, especially if there are many people that have demands on that data. The other important aspect of performance is that of response time. How long does it take to handle each request? It's great if it can handle 1,000 requests a second, but if it takes an hour for each request it receives, that's also a really annoying and makes the database much less useful for people. So another term for this is latency. How long does it take between when you give the request and when you actually get the answer? Obviously, we want low latency. We want short response times when possible. So if both being able to handle many requests as well as being able to handle those requests quickly matter, how do we make databases better? How do we make faster databases? And really, the way that you make faster databases is the exact same way you make any program that you would ever write faster. For instance, run it on a faster computer. Often you're sticking databases on top-of-the-line servers and with caching and doing as much as you can to make sure that it's not hardware limited. Another thing is to use less computational resources. So optimize the code as much as you can, optimize your queries such that it has to do the least amount of work necessary to fulfill the most common types of queries. Another thing is to reduce things like unnecessary I/O, try to get better cache performance, try to keep as much of the database in memory or in even a cache closer to the processor as possible. However, the largest way to get gains in both handling more requests and handling those requests faster is to allow for concurrency. So instead of only allowing one connection to the database, instead of only allowing one person to be talking to the database and getting responses from the database, you allow many different people to communicate with the database at once. And what this means is that we can both utilize the multiple cores, processes, threads. We can utilize parallelization that the CPU architecture can provide for us. And this also means that we can get work done while waiting for the slow parts. And now usually the slow parts are things like human interaction or disk I/O, or some queries take much longer than others. And it'd be really nice is even though there's this one query that's going to take an hour, we can still handle other queries at the same time. So this is all great, and almost every database system supports some level of concurrency. However, what we're going to be talking about for the next couple of weeks is the fact that concurrency is almost necessary in order for databases to be useful. However, it adds a fair bit of complexity, which is the big topic of these series of lectures this week. So one vocabulary word that you're going to need to know, because we're going to be using this term over and over again, is that of a transaction. A transaction is really like, you can think of it as like a unit of execution. The database management system, the DBMS, strives to ensure that transactions are all or nothing affairs. It means that when you have a transaction, think of it as like a short program, which can be usually some number of queries, is that after a transaction is completed, either the transaction succeeds, it reads and or modifies the database, it does what you want, or the transaction is aborted and it makes no changes to the database. So you have one or these two things. And why is this important? Because transactions can do many things in a particular program, and often only doing part of the transaction will leave the database in an inconsistent state. It will, you'll change half of the database, but because the transaction didn't finish, you've left some of the rest of the database that should have changed in the original state, and that's a problem. So the way that you get around this is you promise that a transaction will either go from beginning to end, the all, or it tries and you revert back so that nothing actually happened with regard to the transaction. And so the one kind of guarantee that databases have is that they ensure that incomplete transactions that it goes part of the way and then the power is shut off, or it goes part of the way and then the user is like, oh shoot, something went wrong, please undo what you're working on right now. It ensures that incomplete transactions don't change the database. That's kind of the important rule here about transactions. Okay, so let's talk about some example, really simple transactions. So right here we have the table students. Right now there are two students in the class. There's Tyler and Grant, and they have grades. And there's two transactions that I want to perform. For instance, I need to add myself to the class. I want to insert into students myself with a 3.5. And then Tyler, who's a TA for the class, said, oh, you know what? We've been grading you guys really harshly. So what I'm going to do is I'm going to actually update all of the students' grades in the class and raise it by half a point, which I don't think any of you guys would ever object to. And so these are two different transactions, and they aren't related to each other. But depending on which transaction goes first, we get a different end result. For instance, if transaction A happened first, the student gets added, I get added with a 3.5, and then transaction B takes place, and then everybody's grades go up by 0.5. It means Tyler's grade goes up, Grant's grade goes up, as well as my grade goes up. Okay, and I'm really happy. I now have a 4.0 in the class. However, if transaction B happened first, meaning the student's grades were increased, meaning Tyler's grade went up, Grant's grade went up, and then I got added to the class after that, my grade would only be a 3.5. Now, is this a problem? Which is the correct final table? Should A happen first or should B happen first? And in reality, both are acceptable according to the database rules for transactions. If A happens first or B happens first, that doesn't matter. If you cared, if it was really important that Josh should be added before you update the grades, you should have put them in one transaction that said, hey, there's this one transaction where Josh gets added and then the grades go up. But the fact that these are two transactions means the ordering shouldn't matter. All right. However, things get a bit more complicated if you have, for instance, multiple queries that need to be performed. You're trying to do multiple changes to the database within a given transaction. So let's instead imagine we're back to our original table with Tyler and Grant, and one transaction is needing to add two students in. It needs to add myself and another student named Charles. And there's also transaction B here, which is doing the same thing, and it's bumping up everybody's grade who's in the class. All right, so let's imagine A happens first. If A happens first, Tyler, Grant, Josh, and Charles are all added into the table. Actually, Tyler and Grant were already there. Josh and Charles got added. And then everybody else's grade improved by half a point. Yay, Josh and Charles, both of us got our grade improved. Of course, the other ordering could happen. You could have B then A, in which case Tyler and Grant's grades got bumped up, but Josh and Charles's grade did not. Both of these are, once again, acceptable because you're allowed to reorder transactions. If you have two transactions that occur at the same time, you can do A first or you can do B first. However, you could also get this happening. What happens if we did part of A and then B and then part of the rest of A? So we have Tyler and Grant, and then we add Josh into the database. Yay, I get added in the database. And then we do transaction B. We update all of the students. So Tyler, Grant, and myself, grades went up. And then we finish transaction A by adding Charles in. And this is the big problem here. This is the problem where the transaction rules didn't work. Because what happened is I got an improved grade, but Charles didn't. And that doesn't make sense. There's no, either transaction A should happen in its entirety, or it should have been aborted, but you should not have had transaction A happen partly, other code come in, and then transaction A finish in a way that leaves this inconsistent state. The rule was all of the students in the class should have had their grades bumped up, but what happened here was only part of the class had their grades bumped up because these transactions meshed and hit and ran into each other and intermerged, which is something that databases do not allow. This violates what's called the ACID test. So ACID is one of the kind of fun, silly acronyms in the class. Properly implemented transactions are said to meet the ACID test. These are kind of the rules for what makes a good transactional database. So the letters are, A stands for atomicity. This means transactions have to occur either all or nothing. That's the thing I mentioned before. Either you finish the entire transaction or you abort. So A stands for atomicity, meaning atom, meaning indivisible. I stands for isolation. It means that each transaction must appear to the outside world as if no other transaction was executing at the same time. It's like we did A and then B, or we did B and then A, not mixing them together. D stands for durability. It means that after the transaction completes with either an abort or a success, that change that the transaction made to the database needs to remain there. It can't just go away if the power fails or something like that. The rule is once a transaction completes, that is a permanent change to the database. Now, of course, you can have other transactions that revert the effects of other transactions, but the thing is that that won't happen unless you actually make a transaction do that. There's no, oh, the transaction completed, but later, never mind, actually, the database is just going to decide it's better if that transaction hadn't happened. So durability is basically the database is guaranteed that even if things go wrong later, even if there are exceptions, people give bad queries, even if the power fails, the database has the data stored in a manner that is recoverable. And the letter that I skipped, because of course ACID's not aid, the letter that I skipped was C, stands for consistency. And this is probably the hardest one to understand. And this is the idea that all databases have consistency constraints, which is another way of saying expectations about the relationship between parts of the database. We'll talk about a number of examples as we go on. One that's easy to kind of think about is the idea that, maybe you have a rule that account balances in some sort of bank are never allowed to be negative at the end of a transaction. You're allowed to move money around, but when the transaction is done, nobody has negative money. And the rule is transactions are expected to preserve the consistency of the database. Now, of course, I could say, if I had a database, I could write a transaction that said, give $1 million to Josh. And if you don't have $1 million, suddenly your account goes negative. But as long as a transaction follows the rules of it will never ensure that the balances go negative, then it means that the database will never go into a state where balances are negative. Okay. So with regard to these 4 principles for ACID, when my grade was improved, but Charles's grade wasn't, which of these 4 ACID properties were violated? All right, and so if you aren't confident at this stage, once again, we'll be talking a fair bit more about this. I recommend re-watching the earlier part of the video. But the ACID property here that was violated was the isolation rule here. There was no way that my grade could have been improved, but Charles's grade wasn't, unless these 2 transactions were interfering with each other, unless they were happening and running at the same time as each other. Because it means that the transactions, there's no way that if A happened first and then B, or B happened first and then A, that you could ever get this half improved between the 2 of us. So the rule that was violated was isolation. All right. But because, once again, consistency is the more complicated one, I'm going to talk a little bit more about that before we move on. So another way to think about consistency is the fact that a database always has a state. What is the state of a database? It's basically all the data that's inside it, which is the value for each of its elements. Now, what's a database element? An element is a table and a row, and a database as a whole. It's really just a part of the database. And I say elements to be a bit more general because different databases, especially databases we'll cover at the very end of the class, can have a very different structure than this table row layout. Okay, and so intuitively, we regard certain database states as consistent and others as inconsistent. Now, what do we mean by that? Consistent states satisfy all the constraints of the database schema. Like, in order for a database to be consistent, if you specify that this is a primary key, it has to be unique and it has to be not null. That's kind of taken as a given. The database itself will enforce those rules usually. However, there are often more implicit constraints that are in the mind of the database designer. They're not built into the database code, but they're expectations on how the database should work. So for instance, it's not necessarily a law. There's no software that enforces this, but we often, especially when you're talking about account balance and stuff, have a conservation of money, which means that when you're transferring money between accounts, there should not be a change in the total amount of money in the database. Like if you're moving $100 from account A to account B, there shouldn't be suddenly more money represented in the database than there was before. And then there's other examples, for instance, valid data. So for instance, maybe I have this implicit constraint that I'm not friends with that anybody who drops my class is no longer my friend. Okay? So if I remove a student from the table students, they should also be removed from the table friends, because there should not be any student anybody who leaves my class should also stop being my friend. Now, obviously, there's no rule. Nobody who wrote SQLite would be like, I better make sure Josh's constraint is here. That's a constraint that I have and I enforce. And now, how do I make sure? Well, if the database starts in a consistent state, meaning if there is, $100 in total across all the accounts in the database, and if the transactions never violate consistency, meaning whenever money is moved around, they always move money from one account to another in the exact same amount as before. The rule for consistency is regardless of the ordering of the transactions, the database will be consistent afterwards. And this is called the correctness principle. If a transaction executes in the absence of other transactions. So imagine if we move money from account A to account B in a particular transaction, and it states with the database in a consistent state, then the database will always be in a consistent state after the transaction ends. It means that the transactions are not allowed to change the rules. So even though I could, in theory, write a transaction that was just add $100 to account B, as long as I perform the rules of only writing transactions that move money around, that follow the conservation of money, it means that the conservation of money constraint will be held by the database. Now, once again, these are all kind of lofty topics, and we'll talk a lot about these in more detail in the future videos of this week.